Hello, this is a video presentation on a project titled Integration of a Home Energy Management System, or HEMS, with rooftop solar and Tesla PowerWall to improve demand response in Arizona. This project is for the course titled Demand Response and Renewables Integration in the Electric Power System. My name is Hassan Idris, and I'm an MSc student at ASU. Here is an outline of the presentation that accompanies the detailed project report. References will be made to the report during the course of the presentation as necessary. The presentation begins with a short introduction of the project, followed by the motivation, i.e., the reasons as to why this project is important and why it was selected. After this, a brief outline of the system will be provided, which would touch upon the major areas covered here. The overview of the system will define how the project layout is structured. The operation part of the presentation will explain the working of the system. The presentation ends with a few points described here, which would enable penetration of this project in the existing power grid. To begin understanding the project, let's break it down into smaller, easier parts. The project is based on a few important components, the first of which is the Home Energy Management System, or HEMS. The second important component is the distributed generation resource, here exemplified by a rooftop solar PV system. Other popular residential distributed generation resources, like a wind turbine with a doubly fed induction generator, can also be considered. The third important component is the Tesla PowerWall battery, which is a relatively new player capable of having an important role in power distribution and utilization system. The project involves the integration of these components, and this is to improve the demand response for the utility and power consumers. Finally, the location. Arizona is chosen because it is a place with quite a lot of potential to have an impact in the DR area. To make a reason for this project, we first need an explanation of demand response. This does not simply mean the definition of the Federal Energy Regulatory Commission, or FERC, but to see DR as a transforming resource which has a different meaning for different entities. Historically, the use of DR has been limited to clipping load peaks to continue system reliability and mitigate spikes in prices that could occur on an infrequent and predictable basis, here referred to as potential shortfall areas, which can be flattened out. Lately, though, DR has been under reconsideration for a large number of applications to balance reliability as a result of grid conditions, including shortfall, oversupply, and frequency, that are increasingly occurring on a frequent and unpredictable basis. ANRNOC has coined this term as DR 2.0, as shown here, where the model would potentially identify the role DR can contribute by tackling challenges associated with the growing variable energy resource, or VER. This is especially true for the Western interconnection, after the ambitious plan by the California Renewables Portfolio, or RPS, to include 33% from renewables in the grid by 2020. This brings us to the reasons why Arizona can benefit from this. For at least 3 months in 1 year, more than 4,000 million kilowatt hours are consumed by the retail residential electricity in Arizona, which is shown by the blue trend line here. The overlap of the red line as monthly average temperature shows a relationship between climate and residential power consumption. A third overlap shows how much there is to gain when this DR definition applies to Phoenix, Arizona. This brings us from DR 1.0 to DR 2.0. Refer to section 1.1 in the report for more details. Continuing to base the factors for such a project in Arizona, the aggregate DR potential by state and province in 2020 can be seen here. This picture shows commercial and residential sectors dominate in potential DR resource availability. Residential loads, which are the focus of this project, have a combined 1.1 gigawatt of load decrease potential for contingencies, and about the same capacity for regulatory and load following environments. The energy consumption pie chart shows that Arizona households use 66 million BTU of energy per home, which is 26% less than the average American household. Despite consuming less energy, people in Phoenix end up paying higher dollars per kilowatt hours electricity price than in any other part of the US. Not surprisingly, a big chunk of it is on air conditioning, more than in any other state. The project integrates use of new technologies. For a 10 kilowatt rooftop PV system connected to a 7 kilowatt hour Tesla PowerWall battery for charge storage and powering household appliances during peak load hours, an intelligent home energy management system can be connected to ensure that areas mentioned as potential oversupply and shortfall in the duct chart previously can be flattened out. Refer to section 1.2 in the report. Inside, the three main blocks of the system are the HEMS, rooftop PV system, and the Tesla Powerwall batteries. The HEMS physical structure is typical and is designed as shown here. This block diagram describes the operation of the proposed system, with the load measurement being carried out at the appliance side with the power measurement unit. The data distributing unit can transfer the DR info from the utility company like APS or SRP to the end user. HEMS is fed by the data from the data distributing unit. The real-time pricing details can be calculated with the received DR details. Using Wi-Fi as a communication interface allows connection to the internet. The controller or master controller can turn on and off various appliances used as per the demand response received from the utility side. The various loads like washing machine, air conditioner, lights, heater, etc. can be controlled using this system. Here, lights are given a higher priority as compared to other appliances. The least priority appliances can be operated when there is a low peak to average ratio. In this way, effective demand response management can be obtained with this system. While an isolator can typically isolate or disconnect a switch, here it can turn off the various appliances that are connected to the energy management system to disconnect loads during peak times. A current sensor is used to detect electrical current AC or DC in a wire, and it generates a signal proportional to it. The generated signal could be analog voltage or current, or even digital output. It can be then utilized to display the measured current in an ammeter. Alternatively, it can be stored for further analysis in a data acquisition system or utilized for control purpose. The data acquisition is a process of sampling signals that measures real-world physical conditions, and it converts resulting samples into digital numeric values that can be manipulated by a computer. The data acquisition systems consisting of sensors, signal conditioning circuitry, and ADCs, or analog to digital converters, can convert analog waveforms into digital values for processing in HEMS. The HEMS division is an intelligent system having the ability to learn and adapt as per the patterns and usage of electricity. This project draws on the adaptive neuro-fuzzy learning algorithm developed in a study by Ozturk and Kumar, published in IEEE Transactions on Smart Grid in June 2013, which makes DR decisions based on peak load forecast, differential electricity prices, customers' usage patterns, energy budget, social and environmental factors, and available solar power. This figure shows how the data and control signals flow in the system. The master controller or MC gets the input from the rooftop solar meter, and it projects the energy demand to the pricing controller, which conveys the TOU pricing quantity back to the MC, which then uses Wi-Fi to communicate to the home area network. The consumer can access the data, settings, and status using the GUI or the graphical user interface. Refer to section 2.1 for more details. The Tesla PowerWall is a 7 kWh, 9.5 amps, 3.3 peak watts battery. This is sufficient to power most homes in the evenings using electricity generated by solar panels during the day. This battery is wall-mounted, rechargeable, lithium-ion with liquid thermal control. While it is compatible with both single and three-phase utility grid, it still does require an inverter. Multiple batteries may be installed together for homes with greater energy needs. A 10 kWh weekly cycle version is available for backup applications. The battery has 92% efficiency and a 10-year warranty. Refer to section 2.2 and Appendix A for more details. For a 10 kW rooftop PV system, a typical wiring diagram for this project is shown here, with the PV system connected to the grid with Tesla PowerWall batteries, shown as GR generator. Note that different systems are modeled differently for each residential unit, depending on their energy consumption, client requirement, rooftop size, tilt angle, and several other factors. Refer to section 2.3 and reference 7 for more details. The figure here shows a simple block diagram concept of how HEMS can be deployed using the architecture described in the previous slides. Both hardware and software are an integral part of the operation. When a typical HEMS in a Phoenix residential unit receives a DR signal from the APS or SRP utility, the data center can collect information from both user and utility sides. In this case, prediction and neural algorithms are used to calculate effective critical peak price, CPP, for which high demand calls for high price and low demand for low price. This would enable HEMS to switch between the appliances depending on the need, by using power effectively. The smart Cosmo master controller, as shown here, is the heart of the system. For instance, at a low peak to average ratio, some low priority loads will be turned on to make effective power utilization with managed demand response. The MC for each consumer can utilize a simple adaptive neural fuzzy inference system or ANFIS, by which intelligent appliance scheduling can be done using branch and bound technique. The HEMS algorithm can enable utility and consumers to mutually calculate optimal prices and demand schedules. These results here show the difference in costs when the operation was done by Osterk and Kumar in a test system with and without scheduling algorithm. Refer to sections 3 and 3.1 for more details. While the system described in this project can manage appliance schedules, TOU pricing, and an intelligent energy system to keep total household consumption in check, there may be a few incidents at low demand limit level where customers would have to sacrifice their comfort by using battery power as described here. This then may not power their ACs, washers, and dryers simultaneously. Another limitation is when a DR event can create a high off-peak demand due to a load compensation. The customer would need to again place reliance on their batteries at an unexpected time. Despite these small shortcomings, the results of this project can go on to show that it will definitely be profitable to improve the abandoned peak solutions DR program by APS and power partner by SRP in the long run. Feel free to send any questions or comments at the email address shown here. Thank you for listening.